Hi guys, welcome back to Data Every Day. Today we're looking at a data set of apps from the Apple App Store, and we're going to try to use the data to predict whether a given app will be a game or not. So let's hop into the notebook over here. We're going to use a multi-input TensorFlow neural network to make our predictions. So I'm going to start off with just a standard neural network and show you that we can only get such a good performance with it, and we're going to add an extra input afterwards, and I'll explain more about this in just a moment, that will bring our score up, our accuracy up significantly. So I'm going to import NumPy and pandas just to work with the data, and then matplotlib.pyplot and seaborn for data visualization. Then I'm going to use regular expressions, standard scalar from sklearn, and the train test split function, also from sklearn, for pre-processing the data. Then we will build our model with TensorFlow, and we will now analyze the results with the confusion matrix and classification report from sklearn. So I'm going to go ahead and import that, and I'm going to load in the data using pandas.readcsv. And you'll notice we have two CSV files. This is the main file here, applestore.csv, so I'm loading that in. And you can see we have 17 columns. We have some unnecessary columns here. I think the ID will be unnecessary. And we also have this name, which we'll probably not be using either, because they'll all be unique. Although there might be some useful information here, but for the purposes of the video, I'm not going to use track name. So everything else, though, is fair game. All these will be our features. So let's get started. Before I start, I want to take a look at this other CSV file. So I'm not going to store it in a variable yet. I'm going to just load it up and take a look. And you'll notice this is actually, it contains 3 duplicate columns. The first 3 columns here are contained, but then this also has the description of the app. And this is where the second input is going to come in. So these descriptions actually contain a lot of useful information for trying to predict if a app is a game or not. You'll see we have this is what we're predicting, if the category is games or otherwise. And the reason I'm making it binary, even though we have multiple classes in here, is because the class distribution is really, it's poor. It's really centered on games. So I'll show you that in just a moment. But I do want to include the descriptions. So what I'm going to do is just take this, I'm reading it, and I'm going to do .loc and targeting all rows, and I'm just going to take the ID and app description columns. So that will look like this. And now I'm going to save this in descriptions. So the reason I kept the ID column is because we're going to merge these data frames on the ID column. After we do the merge, we don't need it anymore. But we just want to know which descriptions go with which examples. So yeah, let's look at it right here. And basically, to merge, so I will say merge data frames. To merge, all we do is take the first data frame, which is data, and type .merge, and put in the second data frame, which is descriptions. And we want to specify which column we are merging on, which is going to be the ID here. So with that, you can see we now have all the same features as before, but we now have the app description column on merged onto the data, and it was merged via the IDs, so we know they match up to the IDs. So I'm going to make this our new data. I'm going to overwrite data to be this now. Okay, and now we can start pre-processing data. So here's what I'm going to do. I'm going to create a function called preProcessInputs that's going to take in a data frame and return x and y. Here, y is going to be what we're trying to predict. So that's going to be the prime genre category. So I'm going to get df sub prime genre and make a copy of it, and just this column is going to be our y. Then x is going to be everything except that column. So I'm just going to drop it, prime genre. I'm dropping it from axis 1, which is the column axis, and then I'm going to return x and y like that. So I'm going to split df into x and y. And before I do any of this, I just want to make a copy of the data frame so that anything I perform in this function will be on a fresh copy. Alright, so let's get our x and y from preprocessed inputs. And we're going to pass in data here. And we can take a look. Here's our x like it was before, and here's our y. So let's keep the original data right here so we can refer back. And now all I have to do is put in all my pre-processing steps to this function, and we can see how it updates as we go, comparing it to the original data. So first, let's drop the unnecessary columns. So df equals df.drop, and I'm going to specify which columns we're dropping. We're dropping from axis 1, that means columns. And so we don't need this unnamed 0 column, that's just a duplicate index column, right? What else? ID is no longer useful because they're all unique. Track name is not useful. You could argue that it is, but for our purposes we're not going to use it. We're just going to work with the rest of the data and the descriptions. Okay, so now if I run this, you'll see our data set now no longer has those 3 columns, and this is what we're working with. And everything here looks pretty decent. There's a few bits of information I want to get from the data now, which is, do we have any missing values? So the isNA function will return a data frame that has true or false, depending on if there's a missing value in a given location. We can then sum over, by default this sums over the rows, to get the total number of missing values in each column. So it'll add up the trues and falses, converting them into ones and zeros, and you'll get the total number of trues, or the total number of missing values, by summing over the rows. And you can see there are no missing values in any of the columns, so we don't have to worry about missing values. That's good to know. Next, I want to know how many unique values do we have in each column. So I'm going to get a dictionary that's going to map a column name, which will be one of these, to the length of unique values, so x subcolumn dot unique. This will return a list of the unique values in a given column, and then we get the length of that to see how many we have for every column in x.columns. And now we can see the number of unique values in each column. And right away I notice currency has 1 unique value. If you ever have a column with 1 unique value, you can drop that column. It is not helping you at all. It's not telling us anything about the information. So we will drop it. We can just drop it right up here. Currency. Now we no longer have currency, and we can look at the others. Many of these are numeric columns. So numeric columns we don't have to worry about. They're already already encoded the way they should be. There's no need to do any sort of a manipulation to them. The price is also numeric because this is a continuous range, even though there's only 36 unique values. The rating count total is also numeric. Rating count version is also numeric. The user rating, you could consider this as numeric or as a ordinal feature, because technically there are discrete values you can pick. I think you can only select the 0.5 or 0.0. But we're going to keep it as numeric because it still represents a continuous range of how popular it is. And then user rating version, just the same thing. This version category, this has 10 unique values. 1,500 unique values, but it is not a numeric feature. This is actually going to be different for every app, and it's signifying basically how old the app is. So what I want to do is I want to work with this. I want to create we'll create some new features from it. Create version features. So I'm going to come back to that. We're going to keep going though. Cont rating, I think this is content rating. There are 4 unique values, and they subscribe to a specific order. Right? We have 4 plus, then 9 plus, then 12 plus, and there may be other values in there, but they go in a particular order. So what we're going to do is treat this as an ordinal variable and encode each one of these as an integer in a range. And yeah, it's interesting. There's multiple ways to do this. We could encode them as actual 4s and 12s to give the same sense of spacing between them, which we may do. That's not a bad idea. And then subdevices num, this is just a numeric feature as well. This is the number of devices that are supported. And then iPad SC URLs num. We're not sure what this means, so let's go into the description. And there are descriptions of each column here. So this is number of screenshots showed for display. So that is also numeric, right? Is a count. And then language num, this is the number of languages supported, I believe. Yep. And then this is just, this last one here is a binary column. There's 2 unique values. So whether or not this is categorical or numeric, it doesn't matter, because a binary column, if it's encoded as 0s and 1s, you can just leave it as it is. And then our app description, that's going to take a little separate doing. For now, I'm going to drop it. We will come back and use it though, but for now, so drop app description column. df equals df.drop app desk axis 1. Okay, so now let's deal with this version. This is the only really tricky one. Since it's a little harder, let's just do the content rating first. So ordinal encode content cont rating column. So ordinal encoding, you want to specify an order of all the values in the column. So let's get just that one. So I'm going to get the unique values in the cont rating column. And you can see there are only 4 values, 4, 9, 12, and 17. We want them in that order. So what I'm going to do is create a dictionary that's going to map each value to its respective value. Now what we could do is take 4 plus, and map it to 0. Take 9 plus, and map it to 1. Take 12 plus, and map it to 2. And take 17 plus, and map it to 3. Now this could work, however, it doesn't preserve the spacing between the values. And I don't know how much this really affects it, but I'm going to go ahead and actually just map them to integers instead. Because now, we're going to scale the data anyway, but now there's a relative spacing between the values. Oh, wait a minute. Yeah. Okay, there's 5 in between here, 3 in between here, and then 5 in between here again. So this is good. So yeah, let's go ahead and grab this. I'm going to bring it into the function here. And basically, I'll call this cont ordering. And then all we have to do is take the column and we're going to take the column again, and we're going to call dot replace and pass in the ordering. And if we pass it in as a dictionary like this, it'll actually, the replace function will just perform the mapping for us. So every 4 plus will go to 4, every 9 plus will go to 9, every 12 plus will go to 12, and every 17 plus will go to 17. And so if we run this, take a look, you can see the unique values are now integers, and you can see we no longer have the pluses, they're now in integer form. Alright, so let's do the versions. So this one is a little trickier, but not too bad. Basically what we're going to do is we're going to write a function that's going to take one of these, and it's going to return 3 values. The major version, which is the first value here, the minor version, and the patch version. And you'll notice that not all of the variables have a patch version, and I'm not really sure how important a patch version is going to be, because it changes so frequently, and it's really not anything special. This is really the most important thing. Are we on version 1, version 2, or are we still in beta, like this? And then the second one is also sort of telling us how old it is. Patch version, not really important, but I do want to include it. It's not important, but I'm going to include it. So what I'm going to do is create a function called getVersions. It's going to take in a version. And a version here is going to be a single string like this. So what I'm going to do is use regular expressions to capture only the parts of it that we want. So this website is called regex101.com, and it's a fantastic way to play around with regular expressions and see what works. So I'm going to put in our test string here, and then we can type regular expressions up in the top to target different parts of the string. For example, we can do the caret to signify start of line, and then \d for digit characters, and then plus for digit characters any number of times. So this regular expression says any number of digits in a row starting at the beginning of the line. So if I put any number of digits here, you'll see it captures that whole thing, but the second that something that isn't a digit comes, it stops. So this is basically the regular expression for capturing the major version, right? So if we go into here, we have our version, and we're going to return major ver, which will be our major version. That's going to be regular expressions.search. So this is a module I imported from Python, and you can search a string for a given regular expression, like this. We specify the regular expression, and we specify the string we're performing it on. And then we also want to get the, we call the group function, pass in 0, just to return it as a string, because the search function actually returns a match object. So by doing .group group of 0, we can get it as a string format. Okay, so right here then. Okay, we're going to paste in our regular expression, and let's just test that out. We're going to return major version when we're done. I'm going to try get versions on one of these. So let's grab, what's a good one? Yeah, let's grab this one. Alright, yeah. Grabbing that. We're going to pass it in as a string. And we get 5. Now, this is still a string. You'll see the quotes are around it. So let's actually turn it into a NumPy integer when we're done. And now we'll get it as an integer. Alright, so what I want to do is I want to return the major version, the minor version, and the patch version. So, minor version. This one's a little more involved. We want to get the 3 now. And the minor version is sort of defined by having a period on either side of it, right? Now in the case where we don't have a patch version, it's only going to be the last number. But we need a way to distinguish between the minor version and the patch version. So we're not going to, I'll show you what we'll do in a second, but we're trying to look for essentially a number that's between two periods. And for this, we're going to use a positive look behind statement, which takes the form of this. So this is a positive look behind. And you'll see basically what this is saying is we're going to pass in a value right here, like a period. And this is saying find anything with a period behind it. So let's say digit character, any number of times. Then you'll see that it's finding all the digits that have a period behind them, but for example the 6 isn't being captured because there's no period behind it. However, I don't want the 5, I only want the 3. So what I also need to do is include one of these, which is a positive look ahead. And that's very similar to look behind, except it's saying find something with a given character after it. So here I'm going to put in a period as well. And now you can see it's only targeting the 3. It's saying find any number of digit characters with a period behind and a period ahead. So you'll notice if I put anything in there, it'll still capture that whole thing. And so this is the regular expression to get the minor version. So I'm going to copy that, and I'm going to go in here. So I'll just keep it here for a second, and then I'm going to copy from the line above, and I'm just going to substitute this in as the new regular expression we're using. So now I'm going to return major version, minor version, and I'll return it as a tuple so that we can index. So what I mean is Let's say we want to get just the major version, we'll do sub 0, and that's a 5. If we want to get the minor version, we do sub 1, and we get 10. So now the patch version. Patch version is not that hard. Patch version, we just want this 5 now. We're going to do $sign to signal end of line, and then we're going to do any digit characters right before the end of the line, and that will do it. That's all we need. So let's just grab the first one and then substitute that in as our regular expression, and now this is going to be the patch version. Now return major version, minor version, patch version. So let's just change this to 2, and we do get the patch version. We can make this anything we want, and it'll take that number. So let me just test this out. We have the 0, which is the major version, the 1, which is the minor. Oh, what's wrong here? That's not correct. Uh-oh, this is not correct. So let's take this, something's wrong here. Alright, let's grab this. I'm going to put it in here, and I'm going to see why this is wrong. I'm going to grab this regular expression, paste that in here, and you'll see, uh-oh, it's capturing here. Why is that? It's saying matches. Okay, give me 1 second. I actually want to figure out why this is. Okay, yeah, I figured out what it is. It's very stupid. So the period actually has a special meaning in regular expressions. It's a quantifier, which means it substitutes in for any character. It's like a wildcard. So if we backslash it, then we can actually explicitly reference period character. So that is what we want. So we're going to go ahead, replace this. Now you'll see we get the proper value. Alright, so this essentially will return the major version, minor version, and patch version. Oh, sorry, there's 2. Alright, so what we're going to do is apply this function to every value in here. And this will automatically give us a problem because we have this, right? And so when it tries to find the minor version, it's going to run into an error because there are no such matches with a period on either side in this case, right? There's no 2 periods. So a little workaround we could do, we can say at the top, if version.count period equals 2, then do this. Else, do it the same way, except the patch version is just going to be 0. So in this case, where there are not 2 periods, when there's going to be 1 period, we are only going to get the major and minor versions, and the minor version is actually just going to get this regular expression, which we used for the patch version previously. So if we try this, here, let's try running this on here. Notice that actually the .count, the string function .count, let's say we have a version like this. If we call .count on it and pass in something to count for, it'll return the number of occurrences of a given character. So this is saying if we have 2 periods, we're going to do it this way. And if we don't, which is just going to be the case where we have 1 period, then we'll do it this way. And we'll just give a 0 for the patch version. So let's try calling that. So this currently works the same way. Let's try removing the patch version. And that should return 0. The minor version should be that, and the major version should be that. So that's working well. Now let's try applying it. So all we have to do is say df sub ver is going to... Okay, no, actually what we'll do is df sub major ver, so that's going to be a new column, whoops, is going to be the original ver column with a lambda function applied. Actually, yeah. Wait, no. Okay, yeah, I'm going to do a lambda function because we don't want to return the actual output. Like, I could pass in get versions right here, just apply that function directly, but the problem with this is we don't want all three values, we only want one of them. So I'm going to make it a lambda function that just takes an x and maps x to get versions of x, but with only the first value returned. Then we'll do it for the minor version and the patch version. So this will be minor, and here it will only return the first value 1, which is the second value, and here will be patch, and here we'll return 2. So now we should have 3 new columns, and when we're done, we can remove the ver column because it's no longer of use. Df equals df.drop. Okay, so let's see what happens. Alright, so we got an error. So none type object has no attribute group. So when you get this error using regular expressions, usually what it means is that you notice after we search for it, we call the dot group. If it doesn't find an occurrence, it will not be able to call a group 0 because it won't return a match object. There will be no match, and you won't be able to call this function on it. So what this means is there's something in the data here that is not fitting in with our scheme. And a nice way to figure out what that might be is we're going to enclose this in a try-catch block. So we'll say try doing this, and if we encounter an error, print out the version so we can see what's causing the problem. So now we'll try this again. And now you see it prints out the problematic value at the top. So there's at least one in here that has this IOV prefix at the beginning, and we don't need that. So what I'm going to do is up here, we'll say version equals version.replace IOV, and I'm keeping the space on. We want to remove the space as well, replacing that with nothing. So we're essentially deleting IOV from the string. If it for all the strings, because if there's no IOV, it just won't do anything. Alright, so now let's try it. And we come up with another problem, which is there's also just a V. So we're going to actually just do that again, except we're replacing V with no space. And there's one with a B. So I'm not going to use B as actually a version, even though technically that has some meaning. It's really not that important. So we're going to remove B's as well. And there's one with a capital V. So just a few cases here we're just trying to deal with. And there's one with update with a space after it. So up here, same thing. This is going to be update with a space. And there's one with nothing at the end. So in this case, there's probably only one case like this. We're just going to do the same thing. Actually, no, what we'll do is version equals, we'll say it equals 1.3.0 if version equals 1.3 point. Right, so we're going to just use an if to change it from 1.3 point to 1.3.0, and otherwise we'll keep it the same. Okay, now this should work. It did finish, and you'll see we now have major version, minor version, and patch version for every example. So there was a bit case by case processing here. That's okay. Just if we were going to train this on new unseen data, it would be important that we feed it in. We collect the data in the proper format. All right, so it looks like we're fully done here with everything. It's all numeric, and there are no missing values. So what's left is to feed it into our model. Let's see. Okay. This is looking good. I don't need to see that anymore. We have our x, we have our y, and now let's start training. Well, we'll do modeling first. So I'm going to use TensorFlow, like I said. And first we're going to construct just a really simple model. So I'm going to get an input layer. The shape of a given input will be the size of one of these vectors. So it's of length 14. Also x.shape sub 1. And let's call this x inputs. I actually want to make the train test split first. So we'll use the train test split function from sklearn to split x and y the same way. And we'll specify a train size of 70%. And then that will return xtrain, xtest, ytrain, and ytest. And this actually will shuffle the data too, so we don't have to do it ourselves. So we can include a random state here that will ensure that the shuffle is always made the same way and the split is always made the same way. Okay, so actually let's get the shape of xtrain.shape, and that's going to be our inputs. Then our first dense layer, we'll call it xdense1, is tf.keras.layers.dense. We can give it this. I guess we could just do a classic 64 activations ReLU activation function. Just keeping it very standard here, passing in inputs, and then I'm going to make another one. This will be xdense2, also with 64 neurons and a ReLU activation, but here we're going to pass in xdense1. And then we'll have our outputs, tf.keras.layers.dense. Oh man, I realized I didn't actually encode the labels, so let's do that. So, like I said, their class distribution is really bad. So, let's take a look at the value counts. Value counts will give us each unique value along with how many times they show up. And you can see games has 3,800 values, and the next highest one is 535. So it's a hugely disproportionate number of games as opposed to the rest. If we actually want to find out how much all the rest combined, we can get we'll take the value counts and then we'll sum over it to get the total number, and then subtract just the games amount from that to get the remaining amount. And so you can see it's a comparable number, but it's still, there's even more games than all the others combined. So this here, comparing between games and non-games, seems like a more reasonable classification task than trying to nail down the exact genre of each app. Especially considering that there are some here with only 10 examples, which there's no way, it's very unlikely that we'll get our model to predict this correctly in its current state. There are some methods we could use to even it out if we did want to do a full genre classification task. We could upsample these underrepresented ones, which means like generate new examples by sampling from the existing ones. However, then you're working with duplicate data, and even if you employed various methods, it's a sort of fabricated data. There's nothing wrong with it exactly. It can certainly improve the performance of the model just by exposing it to more of this type. But I should say the other way to do it would be to downsample the games so that we have fewer of these, and then that will even it out as well. But I'm just going to keep I'm going to basically separate between games and non-games. So to do that, we'll just go up here, encode labels, and basically we're going to take just the prime genre column and apply a lambda function to it that takes a given x, which will be a given genre, and x will be mapped to 1 if x equals games, and otherwise it will be mapped to 0. And that will completely accomplish what we're looking for. So I'm going to make that the new column now, like that. And now if we look at y is just a bunch of 1s and 0s. And if we look at the value counts now, actually, we already have that here. It's about even, a little bit more in the games category, If we want to get the exact distribution, we can do y.mean. This works if it's a binary column. Then we see there's 54% ones, and the remaining ones are 0. Alright, so let's get back to the model. So we're only going to output one value. That's going to be the percentage probability. It will be the probability that a given example is going to be classified as a 1. That will imply the probability for the 0. So in a binary classification task, you only need one value, and we'll output a sigmoid activation, which will actually give it a value between 0 and 1. Then I'm going to pass in the output from xdens2, and we can create our model with tf.keras.model. We're going to pass in x inputs. Our inputs will be x inputs, and our outputs will be outputs. Alright, so let's get a little information on the model. We'll print the summary of the model, model.summary, and we'll also graph the model with tf.keras.utils.plotModel. Pass in model here. So here's what it looks like. Very simple, just two dense layers, and it just gets fed right through. We can just name these so that this diagram looks nicer. This will be x input. Here we'll have, we'll just call it xdens1, and then xdens2, and the output will be output. Alright, so now we can see it just gets fed straight through. Very simple model. Now we will train it. So for training, we first have to compile the model. So model.compile. We're just going to use an atom optimizer and binary cross entropy loss, which is standard here. Sorry, loss equals binary cross entropy. And for metrics, we'll use accuracy. We could also include AUC, the area under the receiver operating characteristic curve, which is a better metric for understanding how performance is within each class. Accuracy just gives overall performance, and because we have a 54% class distribution here, not too bad to use accuracy. But this metric, metrics.auc, is very good for dealing with imbalanced data. You could have a very high accuracy on an imbalanced data set, and then have a very low AUC. So let's name it actually AUC, and then we're going to train the model. First, we're going to specify a batch size, so 32 is fine, and the number of epochs to train for. What I'm going to do is train for 50 epochs, and then I'm going to store the model's fit history in history. So model.fit, training on xtrain, ytrain, and then give it a validation split of 20%. Pass in the batch size and epochs as we specified above. And then I'm going to include a callback function. Actually, two callback functions. The first one is going to be, not layers, callbacks. First one is going to be reduce LR on plateau. So this function will actually help the model converge. Based on training it earlier, I noticed that this actually improved the performance, so I'm keeping it. And then we'll also have early stopping. So the early stopping callback will allow us to monitor a given value, namely the validation loss, and we'll specify a patience value, which is the number of epochs that we're willing to wait before stopping the training, and we want to restore the best weights as well. So what this will do is it will keep looking at the validation loss after every epoch, and if it notices that the validation loss does not improve for 3 consecutive epochs, it will stop the training and restore the weights from the best epoch. So I'm going to run that. Oops, what's wrong here? This is usually a problem. Oh wait, are our classes okay? Yeah. Oh, okay. I have to actually perform the split again. I did the encoding before the split, so I think it should work now. Yeah, there we go. Oh, what's going on here? This is terrible. What's happening? Something's wrong, I feel like, because it's just doing like 50% accuracy. Let's just get the results. We can analyze what's happening. Model.evaluate on the test set, x test, y test. Yeah, we're getting a 48% accuracy, and the loss is all over the place. Just make sure everything is good. Let me try. I'm gonna try copying over the code I had from before. Whoops. Huh. Alright, give me 1 second. Oh, I know what the problem is. I missed a crucial step, which is scaling the data. So neural networks tend to perform much better when you scale the data. So I imported a standard scaler at the top, and we're going to use that to scale each column in X to have a mean of 0 and a variance of 1. So that will ensure that each of the columns in our input takes on a very similar range of values, which will not confuse the model as much. We'll get much higher accuracy value. So I'm going to create this new scalar object, and then I'm going to fit the scalar with scalar.fit to the train set only. So I'm fitting to xtrain, and then I'm going to transform xtrain using the fit on the scalar. So scalar.transform xtrain, and then we're going to do the same thing for xtest. Now notice I only fit on xtrain, but I'm going to transform xtest using the fit that I have on xtrain. Okay, so that we should now have a much better performance. Yeah, okay, this is much more in line with what I was getting earlier. So our total accuracy comes out to be about 79.5%. So that's not bad. It's definitely not too bad, but I feel like we can do better. And I just want to get a little more information on our results. So I'm going to make some predicted values. So I'm going to use model.predict on the test set. This will generate just this. You see, will generate a bunch of probabilities for each test example in the test set. So if we actually should use numpy.squeeze on it, because currently it's a 2-dimensional array and we just want it as 1 dimension, so that will squeeze it down to 1 dimension. If you look at that, you'll see now it's 1-dimensional. Still just a bunch of probability values. And what we can do is say ypred equals ypred greater than or equal to 0.5. So what this looks like is just a true or a false based on whether each of those probabilities is over 50%. Note that if it's over 50%, we're going to classify as 1, or saying the app is a game. And if it's under 50%, we're going to classify as 0, saying it's not a game. So what I'm going to do is take this true and false list and we're going to create a new numpy array, but I'm going to specify the data type as numpy.int. So now you'll notice this will just change the trues and falses to 1s and 0s. So that's actually our predictions. Then we can get our true values, yTrue, from numpy.array of yTest. So yTest already has the information. I'm just going to change it to a numpy array and save it in yTrue. So now we can create a confusion matrix using yTrue and ypred. This is a much better way of understanding how we're doing within each class. So I'm going to call it CM, and I'm also going to get a classification report. These are both from sklearn. I'm also going to pass in yTrue and ypred here, and then I want to give it some names, target names. So otherwise, it's just going to show up in the classification report as class 0 and class 1. Just to make it nicer, I'm going to change it to other and games. So if we look at the CLR, the classification report, we have the other class and the games class. And you can see we do fairly well within each class. Let's look at the confusion matrix. So I'm going to create a new matplotlib figure to visualize the confusion matrix with a figure size of 8 by 8, and I'm using the Seaborn heat map to plot the CM, the confusion matrix. Turning on annotations, I'm going to set the minimum value to 0. Turning off the color bar, I'm going to give it a color map of blues, and I also have to format it because by default it will show the values in scientific notation. So this will just ensure that they come as integers. And then we will just show. So it's a little plain right now. I'm going to give it a little more information. plt.xlabel will be the predicted values, and plt.ylabel will be the actual values. And we'll give it a title as well. Confusion matrix. And so, okay, let's just get the class names in there and we'll be good. So we're going to get the x ticks, the tick marks on the x. First we have to specify the position. So we're going to have a numpy.arange. So it's just going to generate 0 and 1. And we're going to add plus 0.5 to each one so that it gets shifted over to the center, like these. Then we're going to give the labels, and that's going to be other and games, just like we had up here. And I'm going to do the same thing for the y-ticks. So now we can see the class names, and we can see the percentage, we can see the counts of our predictions. So here's our predicted values, right? Here are the values we predicted as games, and you can see we got a good number of them correct, right? And then 233 of them we misclassified. They were actually other values, but we said they were games. So these would be the false positives or false games. And these would be, over here, the false others. So here's the true others and the true games. And you'll notice it's okay. This is pretty good. There's definitely not like a huge skew in how like performing better in one class than the other. Maybe a little bit more in games here. And that may just be because there were slightly more examples for games. But like I said, we can do better than this, I feel like. So let's go into what we can do. Now we were given some extra data here, namely this column, the app description column. And so this is a key column. This probably contains a huge amount of information about whether an app is a game or not, because found in the description will be all sorts of keywords that give away what the app is doing. And for example, let's see if we can find a game here. A VR roller coaster, a thrilling virtual reality roller coaster. I doubt we're going to find thrilling in many non-games, right? Probably that kind of word shows up mostly in games. Not just a guess, though. I have no basis for saying that. Just an intuition. But my guess is that there's a lot of rich information in here about whether we have a game or not. So, how are we going to process these descriptions? Well, I want to create a new function here called getSequences. Because currently, if we can't just pass in this string as like into the model, it's not going to work. But what we can do is encode the string as a sequence, and then pass the sequence in. And it's going to be a sequence of integers that we can certainly pass into the model. So let's set up the model first before I get the sequences. The way we're going to have it, I want to use an embedding layer. So tf.keras.layers.embedding is a fantastic, useful layer that basically it's going to take each word in our sequence and it's going to map it to a new place in vector space. And the reason that's useful is because let's say you want to map something to a vector in three-dimensional space. That only requires three numbers to describe where in the space it's going. For example, you could have an ordered triplet like 3, 5, 1, and that will point to 3 on the x-coordinate, 5 on the y-coordinate, and 1 on the z-coordinate. So if we send each word to a new location in three-dimensional space, then each word only requires 3 numbers to represent it. And so this is what's called a dense encoding. It's a really nice way to encode high cardinality data. So what I mean by high cardinality is that if you consider the space of all words, right? So I don't know, we can actually find out how many unique words there are in here. I checked it before. There's about 80,000 unique words in all of the descriptions. So if you think about if we used a traditional one-hot encoding approach, and we had a bunch of zeros, sorry, just trying to get a bunch of zeros here, dot dot dot, 0 0, and then 1 1, right? So a one-hot encoding approach would look like this, where we'd have 80,000 zeros and a single one to refer to which word we're looking at. So this is a sparse encoding. They're sparse because there's so many zeros. So that one could shift around. Maybe this means it's save. Maybe if we remove that and put it here, then it will be 20%. Basically, each one of these represents a different word, and the one means it's present or not. So this requires 80,000 numbers to represent. Each word will require 80,000 numbers. And so that's a lot worse than having a dense encoding, which only requires 3 numbers, right? So we want to opt for the dense encoding. Now the only issue is, where do we send them? Like, we could pick random spots to send them to. But the great thing about this layer here, the embedding layer, is that the model will learn where to send them, and it won't just send them to random spots. It will send them to well, at first it will send them to random spots, but it actually has weights that get trained, so it will learn how to send them to spots that make the most sense for the model. So maybe that means grouping them into similarities, or in some meaningful way. And we're not only going to do it in three-dimensional space. We can do it in as high a dimensional space as we want. Generally, the more complex the data and the more deep the meanings and the sort of like how related the words are to each other, the higher dimension you want. For our purposes, I think a dimension of around 64 to 128 will probably be good. So what I'm going to do is I'm going to set up this embedding layer. And embedding layer will take 3 values. The input dimension, which is essentially the dimension of the original sparse encoding of a given word, which, like I said, is 80,000. I want to limit that down a little. I think using all 80,000 words, it will actually decrease the performance of the model. So I'm going to do 30,000. And we'll specify this later when we create the sequences. Then the output dimension is going to be our choosing. This is how high a dimensional space do we want to embed these words in. And I did 128. That seemed to work well, but other values might work better. I didn't really spend too much time heavily optimizing this model, so feel free to jump in the notebook after I'm done and test out some other possibilities. Then the input length is going to be the length of a given sequence. So we want to pass in a bunch of sequences that all have the same length. We don't actually know what this is yet. So let's go ahead and make the sequences. Right, so we have this getSequences function that's going to take in a list of text. This could be a list, a pandas series, a numpy array, as long as it's a one-dimensional list of strings. And we're going to pass in a vocab length. So we'll give it a default value of 30,000. This will basically just means let's only use the top 30,000 most frequent words. So to get the sequences, we're going to create a tokenizer. This comes from tf.keras.preprocessing.text.tokenizer. And we're going to specify a number of words to use, which will be our vocab length. Right, so 30,000. And so what this does, we can call tokenizer.fitOnTexts and pass in the texts, right? And this tokenizer will look at all the texts, count up how many times each word in the text appears, and then rank them in terms of most frequent to least frequent. The most frequent word will be assigned a value of 1, the second most frequent word will be assigned a value of 2, and so on, all the way up to 30,000, and then it will stop. It will discard the remaining number. So let's return tokenizer.wordIndex. I'm just doing this to show you. Let's say we get the sequences for data sub app description. This is the app description column up here, right? This will return the word index for the tokenizer that we fit to it. And so this is actually the ranking, right? So these first few words probably not so important, the and to, but down here we have probably some very useful, like games is particularly useful, right? I'm sure there's some really rich information here that will be useful in the model. And you'll notice that all of the words have been processed, filtered out any punctuation, and lowercased, so that we get a nice sort of, the tokenizer cleans up the words for us. And the good thing about using a Keras embedding layer is that you don't have to process it so much. For example, you see here we have a 3 and a 4. You may say, well, how is the model going to know they're both numbers? Well, because the model learns where to send the words, it actually has the capability of realizing 3s and 4s sort of go to the same location in our 128-dimensional space, right? So we don't have to worry too much about processing the words if we're using this sort of deep learning approach to word embedding. So after we fit. I'm not going to. Well, okay, actually, let's see the length of the word index. Let's see how many unique words we have. So this should just return the length. Yeah, 82,420 unique words. Like I said, this is way too many to use a sparse encoding for, so we're doing this sort of dense encoding approach. And so I don't really need this because we're specifying how many we're going to use. Once we actually create the sequences, we're not going to use all 82,000. So to create the sequences, we're going to call tokenizer.texts to sequences. And it's going to take in the texts, and let's store it in sequences. And we'll return the sequences so we can see what they look like. So this should only have 30,000 words. It's just taking a moment because it actually has to go in and convert it for all 82,000 words. So you can't actually. Oh man, it's actually generating so many here. You'll see that each word has now been mapped to a distinct integer, and you'll see they're paired up in lists here, right? So each list is going to be a single text or a single description, and then within each list we have the word values. This is lagging so hard because I should not have I should have made it a NumPy array first so it doesn't display the whole thing. Wow, did my notebook just crash? Alright, give me 1 second, I'll restart it. Okay, I restarted the notebook. We have these sequences now. I'm not going to try to display them again. But basically, those sequences only went up to 30,000. What I want to do now is, if you notice, they were all of varying lengths. So I want to get them all to be the same length. And we can use the tf.keras.preprocessing.sequence.padSequences function that will take a list of sequences like we had, and it will pad them with zeros so that they're all the same length. So I want to apply this to sequences, and I'm going to specify a maximum length. So the maximum length, we don't know it. Let's find it out. We can use list comprehension to get sequence for sequence in sequences. So this is just reconstructing the sequences list, but instead of doing sequence, we'll do length of sequence. And this is saying, let's get a list of all the lengths of each sequence. And the reason that's useful is then we can call numpy.max to get the longest sequence, right? And this will be the length of the longest sequence. So let's call that max sequence length. And then the maximum length we're padding with is going to be the max sequence length. I'm also going to change padding to post so that the zeros go on the end of the sequence. And then we're going to return, I'm going to store that in sequences and return sequences. So now I can actually visualize this without it lagging the whole notebook, because NumPy arrays are more kind. So I'm going to pass in data sub app description and get the sequences for it. Let me just store that in seek, right? That will just take probably not too long. I'm going to visualize when we're done. And you'll see it's now a NumPy array of uniform length and width. So if we look at the shape, we have 7,197 sequences, which is the number of examples we have, and each one is of length 771. Now, if we get the max of the sequence, you'll see the highest value in there is 30,000 minus 1. So that's because we specified 30,000 as our vocab length. Alright, so now that we have a function that returns this nice sequence input, we can go in here, and instead of dropping the app description column, we're going to get app description sequences. So we'll call it desk, and that will be get sequences of df sub app desk. Alright, and then at the end we'll return desk along with x and y. Okay, so desk is coming into the environment now. We have x, we have desk. What? Oh yeah, here, down here. We have desk and we have y. And now when we're modeling, we actually want to include desk in the train test split as well. So we have desk train, desk test. And here we're going to put desk in there. Okay. Alright, so now let's fix this up. So this is our embedding layer. I'll call it desk embedding. And the input length is going to be the max sequence length, but it's also the dimension of this width. So that's desk train dot shape sub 1. And let's also include an input for the descriptions. The inputs are going to come in separately from the x's, and then we're going to converge and output like that. So desk inputs is going to be tf.keras.input. The shape here is going to be desk train dot shape sub 1, and we'll give it a name as well. Desk input. And over here, let's give this a name. Desk embedding, and we're going to pass in desk inputs to here. Alright, then this will actually return, because we're embedding the words in 128 dimensional space, it's going to take the sequence and it's going to encode each word, because there's each word in the sequence, right? Each word is going to be 128 characters long. So each word will have 128 characters to represent it, and at the end we'll get a two-dimensional array as our output. So because we're getting a two-dimensional array, I'm going to create a flatten layer, tf.keras.layers.flatten. That's just going to take that two-dimensional array and sort of stack it like this into one long vector. So the name here, desk flatten, and I'm going to pass in desk embedding. Okay, so now we have sort of a vector output from our x and a vector output from our descriptions. So now all we have to do is concatenate them. Concat equals tf.keras.layers.concatenate, and we'll pass in xDens2 and desc flatten. We'll give it a name as well. Concatenate, and then our outputs we're just going to bring in concat. Alright, so now when we specify our inputs, we want to pass in x inputs and desc inputs as our inputs, and output stays as outputs. Alright, so now you can see what it looks like. The x's come in like this, the descriptions come in like this, they get concatenated, and then we make our final prediction. You can see the shapes as they come through. For the x's, we have this 15 features becomes 64 nodes, which becomes 64 nodes, which gets concatenated. The descriptions come in with 771 features. They get turned via embedding into a 771 by 128 matrix. Then that gets flattened into a single vector, and the vector gets concatenated with the output from the dense layers. Then this final one converges to a final value, which is our probability estimate. Alright, so now we'll train. This can all stay the same, only difference is that I'm going to change this to xtrain desktrain. We're passing in both inputs now. And let's see how we do. Oh, what's wrong here? Failed to convert numpy array to tensor, unsupported object type int. Let me just look at desktrain. Looks good. Xtrain. Oh, we forgot to drop it. We actually still have to drop the column when we're done getting the sequences. df equals df.drop appdesk axis 1. Okay. Now we're going to generate these, get our train test split, our scale the data, create our model, and then train. Alright, and this is taking longer to train, but you'll notice our accuracy has gone up substantially. We're actually getting really good results now. That is good to see. So it looks like maybe about 93% accuracy. And the validation loss has started to increase, so it has done early stopping. And now we can evaluate. Oh yeah, we can't pass in x test. We also have to pass in desc test. Alright, we have a 94% accuracy and a 0.98 AUC, so really good. Similar here, x test, desc test. And these are our predictions. Let me get confusion matrix and classification report. We can plot the confusion matrix and print the CLR. And you can see this is really outstanding. Only 49 misclassified games, and only 78 misclassified others. So now we can look at this precision and recall scores. Precision is basically saying out of all of the predicted values, how many did you get right? What percentage did you get right? So out of all the ones we predicted as games, which is all of these, 95% of them lie in the correct classification. The other 5% are right here. Then our recall is out of all of the actual others, so these ones, all the ones that were actually others, how many did we correctly classify? So it was 93%. That's because 93% of the values lie here, and the other 7% lie here. Then our F1 score is just sort of a combination of the two. I believe it's calculated by 2 times precision times recall over precision plus recall. So it's sort of a demonstration of how we're doing in both classes. And then for games, you'll see we have very similar performance. For games, a precision of 93%. I misspoke before. I was talking about the precision as 95% over here, but that was actually for other. So this is the 95% precision. because 5% are here and the other 95% are here. Then our precision for games is 93%, which is this one. 93% are here, the other 7% are here. And we have a 96% recall in games, which is saying out of all the actual games, 96% of them were correctly classified. The other 4% are right here. Okay, so I guess that will conclude today's video. I know it's a bit of a long one, but thank you so much for watching if you stuck through the whole thing. But that will sum up the video. I'll see you guys tomorrow. Have a fantastic day.